You open Google Maps, tap Navigate, and in under a second it tells you the fastest route and estimates you will arrive in 23 minutes. But here's what is truly remarkable. It already knows about a crash on the highway 2 kilometers ahead that happened 4 minutes ago, and it has already routed you around it. No news alert triggered that decision. No traffic reporter called it in. No government sensor flagged it. So how exactly does the system know, and how does it know so fast? Every second of every day, hundreds of millions of Android phones with location services enabled are silently reporting their GPS coordinates to Google. That continuous stream of anonymized position data is the raw material that powers every traffic estimate and every ETA you have ever seen on Google Maps. At peak commuting hours, Google is processing well over 3 billion individual location signals per day from devices spread across every continent. The scale of data ingestion happening in the background of ordinary navigation is staggering. Your phone does not just report where it is. It reports where it is, how fast it is moving, and in what direction it is heading at that precise moment. Strip away the personal identity from that reading, aggregate millions of simultaneous readings from different devices across the same road segment, and you have a statistically robust, real-time ground truth of exactly how fast traffic is flowing on every road on the planet. The genius of the design is that the sensors were already in everyone's pocket, and they cost Google nothing to deploy. The data pipeline begins on the device itself. When Google Maps is open and active navigation is running, your phone transmits a location ping roughly every few seconds. When the app is in the background, the reporting frequency drops automatically to conserve battery life, but the data still flows. Each individual report contains a precise timestamp, a latitude and longitude coordinate accurate to approximately 3 meters, a velocity reading derived from the GPS Doppler shift between consecutive satellite signals, and a compass bearing. There is no name attached, no account identifier, no browsing history, just an anonymous dot moving through space and time, contributing to a collective picture. On Google's infrastructure side, these billions of pings per day flow into a massive distributed stream processing system built on technology conceptually similar to Apache Kafka for high-throughput log ingestion and Apache Beam for stateful transformation pipelines. Every ping lands in a partition log keyed by a geohash, a short alphanumeric string that encodes a geographic tile roughly 600 square meters in area. This sharding strategy ensures that all device data for a given road segment consistently lands on the same processing node, eliminating expensive cross-partition coordination and allowing the aggregation to run with very low latency. At any given moment, there are thousands of such processing nodes running in parallel, each responsible for its own slice of the global road network, all updating simultaneously. Within each geohash partition, a sliding window aggregator continuously computes the median observed speed of all device pings received in the most recent 90-second window. If 200 phones in a 1-kilometer stretch of motorway are simultaneously reporting 12 kilometers per hour instead of the normal 100, the system flags that entire segment as severely congested within about 2 minutes of the slowdown first appearing. That 2-minute end-to-end detection latency, from road event to map update visible on driver screens, is the beating heart of what makes the real-time traffic layer practically useful. The 90-second window length is a deliberate engineering trade-off. A shorter window would be more responsive but also noisier and more susceptible to false positives from a handful of phones stopped at traffic lights. A longer window would be smoother but would miss rapid onset incidents like a sudden multi-vehicle collision. Raw GPS data, however, is noisy and imperfect. Phones in dense urban canyons bounce satellite signals off tall buildings before receiving them, a phenomenon engineers call multipath error, which can place a reading tens of meters away from where the device actually is. A single corrupted ping can appear to show a car teleporting 400 meters in 1 second. Google filters this with a probabilistic technique called map-matched hidden Markov modeling. Each incoming ping is snapped to the statistically most likely road position, given the entire sequence of prior pings and the known road topology, and readings that are geometrically impossible given the local street network are discarded before they ever reach the aggregation layer. Speed data alone is not enough to predict what traffic conditions will look like 15 or 20 minutes from now. This is where years of accumulated historical pattern data become critical to the system. Google has indexed a deep archive of traffic readings into a fine-grained time-of-day and day-of-week model covering every road segment globally. A Tuesday morning at 8:15 on a specific stretch of motorway has a highly predictable speed profile derived from thousands of statistically identical Tuesdays. The live prediction system blends the current 90-second window of real readings with this historical baseline using a weighted moving average, leaning heavily on live data when the two agree, and falling back gracefully to historical patterns during data-sparse periods like 3 in the morning when few phones are on the road. Incident detection runs as an entirely separate classification layer, operating in parallel with the speed aggregation. When a cluster of phones simultaneously decelerates sharply from motorway speed down to near zero within a 200-meter zone over a 30-second window, an anomaly classifier is triggered immediately. The classifier cross-references against road geometry. Is there a known junction or roundabout at this location that could naturally explain a vehicle stop? Are adjacent segments showing normal flow, suggesting the slowdown is localized rather than systemic? If the deceleration signature is isolated and statistically unexpected given the time of day and day of week, the system automatically raises an incident alert. No human reviewer is involved at any point. The classification runs entirely in software, and the orange incident marker appears on the map within under 3 minutes of the real-world event occurring. Google also ingests a significant range of external corroborating data feeds that supplement and validate the device-based readings. These include loop detector sensors embedded in road surfaces operated by national highway agencies, traffic camera feeds processed through computer vision models trained to detect queue lengths and stopped vehicles, weather service APIs that correlate measured precipitation levels with statistically expected speed reductions on each road type, and civic event calendars that proactively flag stadium concerts, marathon closures, or major protests many hours in advance. Users of the Waze platform, which Google owns, also contribute manual incident reports and speed trap confirmations that feed directly into the same underlying model. Each external data source is dynamically weighted in the model based on its demonstrated historical accuracy on that specific road segment. Roadside induction loop, that has been consistently reliable for 3 years, receives high weight. A newly installed sensor is held at lower confidence until it accumulates a sufficient performance history to be trusted at full weight. The routing engine takes all of these live edge weights and solves what is fundamentally a variant of the shortest path problem, but across a directed graph with over 50 million nodes that is partially reweighted every 30 seconds as new traffic data arrives. Google uses a graph contraction technique called contraction hierarchies, in which topological shortcuts across the static road network are pre-computed offline, and only the dynamic traffic weights on individual edges are updated at query time. This separation of static structure from dynamic weights makes real-time route queries fast enough to complete within a few hundred milliseconds even for cross-country journeys spanning thousands of kilometers. The routing engine takes all of these live edge weights and solves what is fundamentally a variant of the shortest path problem, but across a directed graph with over 50 million nodes that is partially reweighted every 30 seconds as new traffic data arrives. Google uses a graph contraction technique called contraction hierarchies, in which topological shortcuts across the static road network structure are pre-computed offline during nightly batch jobs, and only the dynamic traffic weights on individual edges are updated at query time with the live data. This clean separation of static topological structure from dynamic congestion weights makes real-time route queries fast enough to complete within a few hundred milliseconds, even for cross-country journeys spanning thousands of kilometers of road network. One of the subtler and often overlooked innovations layered on top of the traffic model is the departure time recommendation. If you look up directions but do not immediately start driving, maps may suggest leaving in 18 minutes rather than right now, because the historical model predicts the next traffic wave on your route will have dissipated by then, saving you potentially 15 minutes of sitting in a queue. This is forward-looking predictive scheduling built entirely on probabilistic traffic modeling. It requires no knowledge of your personal calendar or your intentions. The system is simply asking, given what we know about how traffic behaves at this time on this day on these roads, when is the optimal moment for this particular journey to begin? Taken together, what Google has built is a system that is not merely reactive to traffic events but genuinely predictive of them at scale. It sees the concert crowd beginning to leave a stadium 20 minutes before the first car joins the queue you will encounter. It knows with high statistical confidence that the school run begins at 14:45 on weekday afternoons. It models how a single lane closure on a feeder road ripples backward through upstream intersections across an entire metropolitan network using fluid dynamics-inspired propagation. And it executes all of this continuously across every classified road in over 220 countries with no human operator in the loop at any stage. That is how Google Maps predicts traffic. Thanks for watching.